So hello and welcome once more to another module of FS131 Sensory Evaluation. This time we'll be discussing Module 6, Measuring Responses. Take note that this may have a lot in common with the previous review on statistical analysis, but this time we'll try to focus specifically on those relating to the sensory evaluation tests that we do. So first, we'll review the different types of data and how they are measured in specific relation to sensor evaluation. And again, reviewing hypothesis testing more in depth this time. And then we'll be looking at scaling techniques in preparation for the scaling exercise that you're supposed to do. So when we say data, this refers to the collection of observations. In this case, it would refer to the responses of your panelists primarily in terms of the answering the demographic sheets and answering the questionnaires related to sensory evaluation. And of course, measurement refers to the process of determining the value or label of the variable based on what has been observed. So the value or label is a term that we use, especially when using software like SPSS. Again, this puts us into perspective when we look at the aspects of sensory evaluation: evoke, measure, analyze, interpret. So measurement refers to that specific moment of collecting that data or information, such as when your panelists are doing sensory evaluation and are answering the questions that you've put forth. So in food science, or in any science for that matter, we measure a lot of things. But in sensory evaluation, we also measure human responses, which are not necessarily based on the 7 base SI units. However, in this case, most of the examples are physical in nature, except those relating to microbial population counts. Take note that each of these values can either be interval or ratio in nature. So when we have a scale, we're talking about those which have divisions and labels with anchors, which identify the points in the scale. So for example, maybe you've encountered from as young as you were, on a scale of 1 to 10, judge this and that, or perhaps when you see judges judging contests raising their scorecards, that's some sort of scale wherein one number represents the lowest score and one number represents the highest, and usually there are qualitative values associated with those numbers. Anchors, on the other hand, are those points on the scale which have the predetermined numerical or qualitative values. So for example, this scale here has 5 anchors, 1 for strongly disagree up to 5 for strongly agree, and so on. So generally, sensory evaluation data are classified into two types: numeric and non-numeric. So when you have numeric data, this could either be discrete, such as if you're gonna be asked how many times do you eat rice in a day as part of your demographic questionnaire, then you couldn't really answer 1.5, right? It doesn't mean anything. On the other hand, there are continuous numbers which could have any value, such as if you are being asked how many hours of sleep do you get in a day, you may want to answer 3.5, 3 3/4, etc. Or, of course, if you're gonna take readings like temperature, then of course that could have an infinite number of points in between the whole numbers. On the other hand, you have non-numeric data which occur mainly in your demographics, such as if you are being asked your name, or if you're being asked comments for the sensory evaluation, which obviously would have to be in sentences which normally don't have numbers. Numeric data can exist either as interval or ratio data, as we have discussed before. And even though both of this can exist as continuous information, the difference is in having a true zero. Interval data deals with those that don't necessarily have a true zero, such as temperature in Celsius. Okay, this means that the interval between two values are numerically equivalent. So if, again, you have a temperature of 10 degrees Celsius versus a temperature of 20 degrees Celsius, then that has an interval of 10 degrees Celsius, which is equal to the interval between 20 degrees Celsius and 30 degrees Celsius. On the other hand, that doesn't mean that 20 degrees Celsius is twice as hot as 10 degrees Celsius, or that 40 degrees Celsius is twice as hot as 20 degrees Celsius, because you don't have a true zero, and that means you cannot multiply the values, but you can add and subtract them to get the intervals, and that's where the word interval comes from. In contrast, ratio data has a true zero, meaning you could treat the data as ratio or as multiples. So for example, when you say I weigh 50 kilos and you weigh 100 kilos, for example, then that means you weigh as much as I do. And if my son weighs 10 kilograms, then I weigh as 5 times as much as he does. So you could use ratio to quantify how much more something a value is compared to the other. In such cases, you can use multiplication and division on your data. Again, for the non-numeric data, those are the nominal information, such as pretty much everything you put on your demographic sheet. Of course, these could be counted. Again, you could say how many of the panelists were male or how many were female, or how many of them, what percentage of them reside within Quezon City, or how many of them have eaten balut before. So those are examples of nominal data which you can collect and use in your data correlation, regression, tabulations, and so on. So ordinal data, again, as a review, are those which may or may not have actual values attached to them, but in a way can be arranged, such as when you use words like slight, moderate, and strong. Now, the reason why ordinal data cannot be treated like interval data, even if they are given numerical values, is because the distance between two arbitrarily assigned numbers attached to descriptive words cannot be easily measured. So for example, you say that slight is 1, moderate is 2, and 3 is strong. You are not sure if the use of those words do translate to an interval or ratio difference which are equal. Like if I have a slight versus moderate, is the difference the same as moderate and strong? Or if it's just 1, 2, 3, does that mean that a strong intensity is 3 times as great as a slight intensity? You actually cannot do that. Think of it this way. If you are ranking, for example, students, you rank the valedictorian as first, second, and third. However, you may not be sure if the average of the first person is 90, while the second person's average is just 50, and the third is just 49. Therefore, even though they are ordered first, second, and third, the difference between the score of the first and the second is very high, whereas the difference between the score of the second and third is marginal, and therefore you cannot thus use parametric statistics on ordinal data, among other things. So one pretty good use of classifying data is to make sure that you are using the proper statistical tools for them. Just because they're numbers, it doesn't mean that you can use any statistical tool that can be used on numbers. Again, just to look at the nature of data, this is a simple table that you could use. Take note that this does not take into account count data, which is a way of using nominal information, wherein it's a yes/no thing, like you just count whether or not uh, something or a certain person is under that bin, and then based on the counts, you look at the probabilities, such as how many individuals got the correct answer, or what proportion of the panelists got the correct answer, or what proportion of the panelists meet a certain criteria. So these terms, nominal, ordinal, interval, and ratio, are commonly referred to as levels of measurement. So when you're asked what the level of measurement is, it's usually one of the four. And determining the level of measurement usually allows us to analyze a statistical data set properly, because each sensory evaluation test or tool that you use specifics a data set from a certain level of measurement, and therefore or a combination thereof, and you should know how to use the proper test for that. Then one way for me to remember this is to remember NOIR, or the French word for black, as an acronym to remember their order. And this is a summary of what they are along with examples. What's important for us to learn is that each one of them has a certain method of analysis applicable. So for nominal, again, you count and you cross-tabulate to match. For example, again, if you want to look at compare the scores or the sensory acuity of males versus females, or the consumption patterns based on a certain income bracket, although income bracket of course could also be ordinal to a certain extent. All right, for ordinal, we could use anything used for nominal, plus medians and quartiles, measure of central tendency, or not just quartiles, but any of those that divide your data into ordinal strata, like quintiles, one-tenths, etc. You basically just arrange your data in order and then divide them into equal parts. Like for quartiles, it's the upper one-fourth, the second one-fourth, the third one-fourth, and the bottom one-fourth, and so on. For interval data, you may use mean and standard deviation, correlation, and analysis of variance. And for ratio data, you could use the same. However, you may use those related to ratio, such as geometric mean and coefficient of variation, because the percentages are geometrically related, such that having a CV that is twice the other would tell us a lot about the ratio data that you have collected. In terms of scale use, so this is typically how we use the scales. For interval and ratio, those are scoring tests. Ranking and rating tests belong to the ordinal classification, while nominal data are usually just used to classify. So as mentioned, normally, since nominal data in sensory evaluation are answers to demographic information that are collected prior to the start of the test to help correlate or cross-tabulate the gained information. So these are following examples. And we usually use this in specific relation to our what do you call this? Our sensory evaluation test. So for example, if you are testing for chocolate drinks, you might want to ask if the persons are familiar with chocolate drinks in the market, or to ask them, let's say, what type of rice cakes they have already eaten or are familiar with. So ordinal data can be used in a number of ways. They may also be used to collect demographic information such as your income bracket, whether you earn between, your family income is between less than 10,000 a month, between 10 to 50,000 a month, and so on. Or you could also use them in sensory evaluation, such as the case wherein you are asked to rank samples based on a certain attribute, such as preference or intensity of something. So the moment you are comparing at least two samples in terms of preference or attribute ranking, then you generate ordinal data. So in most cases, the scales that we use, especially if we just made them up, like the smiley scale, it's best to treat them as ordinal data because we don't actually know if there are equal intervals between these slight changes in facial expressions. Again, these smiley scales are typically used when dealing with children and other young sensory evaluators. So in such cases, we treat the data as ordinal even though they appear on a scale which others might assume to be at least interval. Take note that there are pretty much no ratio scales, or very few of them exist because it's hard to verify the veracity of such scales. So as previously mentioned, the specific 9-point hedonic scale has been tested to generate more or less interval data such that the anchors attached to the numbers have a psychological distance which are roughly the same, such that between dislike very much and dislike extremely, the difference of quantified liking difference is pretty much the same as between like slightly and like moderately. So take note that if you would try to translate this into, let's say, Tagalog, um, then you would probably end up with a scale that is no longer interval in nature because you used words that weren't tested psychologically for their psychological difference. There are other types of interval scales in sensory evaluation. However, there are very few of them. The way we create interval scales from scratch sometimes is to say um, test the actual samples with known values. Let's say if you're looking at sweetness intensity and you control the amount of sugar, so um, you make a scale based on that and you adjust the numbers on the scale based on the intensity, and you let the panelists adapt. For example, if one would be 1% sugar and two would be 2% sugar, you have to train your panelists that this is what 2 means in terms of sweetness. Otherwise, you'd end up with only ordinal scales. So ratio data is pretty rare in sensory evaluation. Most of the examples are those measurable in physics, such as absolute temperature, physical dimensions, and so on. Like a 1 centimeter long um, piece of fruit is half as long as a 2 centimeter piece of fruit, for example, or 10 seconds is twice as long as 5 seconds. That's why they're called ratio scales. They have an absolute zero. For air pressure, of course, you have to use absolute pressure. Um, in terms of sensory evaluation, what examples do we have for ratio data? So usually in what we call magnitude estimation, um, the panelists are trained to give responses based on their ratios. So again, this is 2 times as spicy as this one. This is 1.5 times as sweet as the previous sample. So through agreement and comparison, they try to develop their skill in thinking in ratios. Okay, like this is twice as smooth or twice as hard as the previous one. Of course, there is uh, room for error in that, such as when your training is not enough, then they might say that something is twice the intensity of the other when in fact it is not. So don't expect us to use ratio data in our semester in sensory evaluation because you won't have enough time to be trained for that. So before we've looked at the parametric and non-parametric. Again, when you have parametric um, tests or data, so these usually refer to those in the interval or ratio measurement. And one of the main assumptions we have is that there is a normal distribution. So actually, it's possible for you to have interval or ratio data and still be considered non-parametric. And that is when you don't subscribe to the parameters or the data is not normally distributed. So of course, there are tests that we can use statistically to determine if the data is normally distributed, but most of the time we just assume to use parametric tests based on whether or not the data obtained is interval or ratio in nature. Pretty important thing to know is that the data being truly interval or ratio is not just dependent on the scale, but on the acuity of the panelists as well. So for example, if you are using descriptive tests and the scale themselves are considered interval or ratio in nature, but you put in untrained panelists who were not calibrated to answer in accord to the same or respond in accord to the same stimulus with the same with the same value, then in reality the data collected from there will be ordinal at best, in which case you use non-parametric statistical analysis tests. Because non-parametric tests don't require any assumption of parameters or normality of distribution. Typically, they say that whenever possible, parametric tests give better results. However, there is no point in using them if they do not meet the criteria. Okay, so one thing you have to know that when using instrumental data, typically these are parametric in nature. So for example, you are correlating the pH or titrable acidity of your juice samples to, let's say, the perceived sourness, then you can use parametric tests to process your data on pH and TA. On the other hand, if you are using mostly consumer sensory evaluation tests, you would most likely end up with non-parametric data, except perhaps when using the 9-point hedonic scale or any scale derivative similar to it. In terms of sensory tests, when we are doing difference tests, this is basically asking which sample is the same or which sample is different, to which the answer would be a certain sample, like this sample is different or this sample is different, and then you just count the number of correct answers. That would be an example of the need to use a non-parametric test. On the other hand, a descriptive test with trained panelists may generate either ordinal or interval data depending on the level of their training and how the scale is made. For interval data, generally we use parametric tests, although you would want to err on the side of caution, and if ordinal tests are being or ordinal data is being generated, then you might want to stick to non-parametric tests. Again, when we consider statistical tests, the term population refers collection of all elements considered in a statistical inquiry, such as all of the people who could possibly fit your criteria. If, for example, you're saying that um, your population is composed of all the senior citizens which may want to try out a certain brand of senior citizens chocolate beverage. On the other hand, because it's nearly impossible to test an entire population, we resort to sampling in the assumption that having a large enough sample would adequately represent the population such that the results of the survey of the sample would reflect the result in the population. And this is the basis for the social weather station surveys that are usually conducted, wherein they would tell you that for Metro Manila, they chose n number of households and that the result with a certain margin of error would represent the political views of the whole population. Of course, we could argue that these are possibly politically motivated and could have introduced some statistical errors in the process. But nonetheless, we try to do the same with sensor evaluation, although we want to make sure that we minimize the errors. So despite us not being full-fledged statisticians in the sense that we did not study a Bachelor of Statistics course, generally, we want to study the basics and also apply any rules of thumb in terms of how the population would be reflected in our sampling. Okay, so we of course want to study at the very least the different types of sampling methods that we've seen before and the advantages and disadvantages of each one. And we always take our results with a grain of salt, knowing the limitations they have in actually telling us if they do represent the population's opinion regarding food. So again, the distribution refers to the form and shape of the generated curve, which usually gives us an idea into the variability and whether or not this would approximate the normal distribution. Although I don't think we usually do this in our regular sensory tests, such that you um, generate frequency distribution curves for responses. It's still a good thing to do, especially if you want to look at the veracity of our information. Luckily, these things could be done through our statistical software with a click of a few buttons, as long as you know where to click and how to process your or how to encode your data in such a way that makes it easier for the software to do so. If we are to assume a near infinite number of sample units, the distribution would typically approach that of a bell curve, wherein at the mean there would be the most number of responses and it would taper equally on either side as the value decreases or increases from the mean. So we could consider this as a map or model of how data points are spread out. And we take note that at different sections under the curve, there are large variations in the area that are covered, such as, for example, in this section, those with 50 to 70 milligrams per 100 gram calcium content cover a very small area as compared to just the area here from 85 to 100. So typically, these population curves might represent, for example, instead the hedonic scale ratings, like the mean would be the whatever that would be, like say it's a 6 or 7, and then um, a lot less people would give values higher than the mean or lower than the mean as their response. So remember that we assume a normal distribution whenever we are using our statistical test, because all of those statistical tests are based on the assumption that a certain value away from the mean has a certain probability of happening, and therefore we base our statistical test on that, on the probability that a certain value or set of values could occur in relation to a point of comparison. So for example, if you are comparing two products A and B, each with a mean and standard deviation in terms of liking, for example, comparing them for statistical significance or for statistical difference means that you are more or less comparing how their population distributions would look like and what would be the odds that these two population distributions are the same. So typically, we could say that two samples with very close means and standard deviations that overlap are not likely to be statistically different. But of course, you have to test to be able to be sure about it. So for population distribution following the normal distribution, the center would be the mean and median and mode as well. So if it's not a normal distribution, it's possible for the median and mode to be different from the mean. And then towards the side, we could see the variance and standard deviation. So typically these horizontal lines represent how many standard deviations away from the mean a certain value is. Again, the statistical significance for any normally distributed data set is that the mean plus minus one standard deviation generally accounts for a bit more than 2/3 of the data set. Therefore, if you have a population of 100 and you have a mean plus minus one standard deviation of a certain value, say the hedonic rating is 6 plus minus 1, then that means 68% of the population is expected to give a value, a response between 5 to 7. And within two standard deviations, you expect 95% of the responses to fit within that. And within three standard deviations, you expect nearly 100% of the data to fit within that. So again, this has been discussed previously. The z-value simply tells you how many standard deviations away a certain single individual point or value or response is from the mean. And therefore, the higher the z-value is, okay, the more distant that value is from the mean, which may indicate that response as being an outlier. So again, just another example of converting or standardizing any individual value into a z-score, just using the equation. If, for example, in this case, we have analysis of samples and what their calcium content is. So you just plug it in the equation, subtract the mean from the value in consideration, and divide it by the standard deviation to get the standardized score. A z-value of 2 means that it is 2 standard deviations away from the mean. Positive means it's greater than the mean, negative means it's less than the mean. So typically, again, the use of the z-value is to translate this into a certain p-value that would translate into what are the odds that this value as an individual value would occur if the data set would indicate that this is the population population distribution rather. So example, again, we did compute that the z-score obtained was 2. and because it's positive, it's to the right of the mean. So we can now look at the probability that this would occur. Although we could, of course, imagine this to be a smooth bell curve and then adequately locate that to be within the 2 standard deviation mark. So there are typically two approaches um, to this. Okay, so the chance of getting a z-score of 2 or higher in this case, which means you get a calcium value of 130 milligrams per 100 grams or higher, could be calculated either through using the z-score table or the negative z-score table. If you use the z-score table, then you must calculate for 1 minus p. But if you're going to use the negative z-score table, then you could use the p-value directly. Okay, and based on the z-score of 2, if you get that the corresponding p-value is 0.02275 or around 2.75% chance of occurrence, or sorry, rather 2.28% chance of occurrence. So again, remember that parametric data assume normal distribution in that all of the calculations done in those statistical tests are made on the assumption that the normal distribution curve of the population of the responses he collected would look like a normal distribution curve. And thus the importance of knowing the population distribution and normality is on the basis of knowing that we can statistically analyze or elucidate certain parameters of the data set based on that. So again, when you have a population distribution, if you take random samples from it, or take samples randomly, then most of those samples should fall within the central region, within either the 1 standard deviation or at most the 2 standard deviation area. And take note that for a normal population distribution, there is symmetry in the curve as well as a well-defined peak at the top. So again, we've discussed skewness and kurtosis before, and what's important is that our data should approach a normal curve. Again, just to remind us that the more samples are taken from the population or the higher our sample size is, then the more normally distributed the generated curve should look like. And the more that the sample data set approximates the population data set in terms of central tendency and standard deviation. And the sampling distribution should have the same mean as the original distribution, but a somewhat smaller spread. So you should at least have a large enough sample such that their means are on the same area. However, they are not quite as spread as this one, perhaps.